We're in Rosen, Discrete Mathematics and its Applications, section 10.7 on planar graphs. Here I want to go over the proof of Euler's formula. This proof is in your text, but I figure it might be good to go through it together, written out. And so if I have G is a connected planar and simple graph with E edges, V vertices, and R regions, and a planar representation, then Euler's formula says that R is equal to E minus V plus 2. And we want to do a proof by induction using the number of edges in the graph. Okay, so first I need to make a claim that if I've got a graph with n edges, it's connected, planar, and simple, I can build up G from a starting point of just the complete graph with 2 vertices. And then the way I would do that is in some sequence, I would add new vertices, each with an edge, or just new edges between existing vertices. Okay, and that gives me a way to do induction. So my base case will be K2, 2 vertices with a single edge between them. Really, that should be K2 is correct, but it's the proposition is P1 because I only have a single edge. All right, has E1 is equal to 1, V1 is equal to 2, and there's only one region. The plane is not split into any more regions than that. And I'll calculate E minus V plus 2 is 1 minus 2 plus 2 to equal 1. So EF holds for the case of one edge. The EF is the Euler's formula. All right, so I'll assume with an inductive hypothesis PK is true. That is, the graph with K edges built up from K2 has RK is equal to EK minus VK plus 2. And we want to show that our inductive hypothesis implies PK plus 1. And the K plus first edge can be added in one of two ways, as we had suggested earlier. All right, so case 1, we're going to add a vertex and an edge. So that means VK plus 1 is one more edge than VK. EK plus 1 is also one more edge than EK. But a new vertex is added into an existing region, and the new edge connecting the vertex to the graph doesn't divide that region. So the number of my regions doesn't change in case 1. That is, RK plus 1 equals RK. And then I'll solve for VK as VK plus 1 minus 1. Solve for EK is EK plus 1 minus 1. And RK again is RK. Under the induction hypothesis, RK equal EK minus VK plus 2. So I will substitute in there to get RK plus 1 equals EK plus 1 minus VK plus 1 minus 1 plus 2. These minus 1's cancel out to give me R sub k plus 1 equals EK plus 1 minus VK plus 1 plus 2. So PK plus 1 is implied in case 1. Let's look at case 2 now. In case 2, we add a new edge between existing vertices in a graph with k edges. In that case, my number of vertices doesn't go up, so VK plus 1 equals VK. But the number of edges goes up, EK plus 1 equals EK plus 1. And since the new edge must cut across an existing region, the number of regions in a new graph increases by 1. So RK plus 1 is equal to RK plus 1 for the new region. So then I'll solve for the sub k's. VK is equal to VK plus 1. EK is equal to EK plus 1 minus 1. RK is equal to RK plus 1 minus 1. Substitute those into the Euler's formula under the induction hypothesis. I get RK plus 1 minus 1 equals EK plus 1 minus 1 plus VK plus 1 minus 2. These minus 1's cancel out to give me Euler's formula for the inductive step. So PK plus 1 is implied By case 2 also, there's no other cases, so we have proved theorem 1 by the principle of mathematical induction.